the sun is not what you think. Almost everything you were taught about what happens up there is wrong. NASA flew a spacecraft through its atmosphere. And, as if that wasn't strange enough, what NASA found when it touched the sun changes everything. We thought we knew about our star. So, let's go there. This is the first image ever taken from inside the sun's atmosphere. It was captured by a NASA spacecraft called Parker Solar Probe during its flyby on Christmas Eve, 2024. And this is what the solar wind looks like up close, racing outward from the sun's corona, recorded by the same spacecraft just hours later. Now, the problem with the sun before this mission is that we had never actually been there. We had made predictions, but every single one of those predictions was based on distance, and distance hides things. On April 28, 2021, during probe's 8th flyby, it crossed a boundary that no spacecraft had ever reached before. It is called the Alfvén critical surface. This is the invisible frontier where the sun's atmosphere ends and the solar wind truly begins. Below this boundary, the plasma is still physically connected to the sun. Magnetic waves can travel back and forth between the surface and the surrounding material, binding it to the star. Above it, the solar wind breaks free and escapes into interplanetary space. It is the line where the sun lets go. Until Parker Solar Probe crossed it, no one knew what this boundary actually looked like. For decades, scientists had modeled it as a smooth, roughly spherical shell surrounding the sun, a clean edge. What Parker found was very different. The Alfvén critical surface is wrinkled. It has spikes and valleys. The spacecraft passed into and out of the corona several times during a single flyby, dipping in, popping back out, then plunging in again. And the cause of those wrinkles turned out to be something scientists had observed from a distance but never measured directly: coronal streamers. These are giant plumes of solar material that rise up through the sun's atmosphere, extending millions of miles outward. From Earth, during a total solar eclipse, they appear as the wispy, delicate structures radiating from the sun's corona. But up close, they are massive rivers of plasma that push the Alfvén surface outward wherever they form. The spacecraft was flying through material that was still physically bound to our star. It was making the first measurements from within the atmosphere of a star. On October 29, 2018, just a few months after launch, Parker Solar Probe had already become the closest artificial object to the sun, breaking a record set by the Helios 2 spacecraft in April 676. Since then, it has broken its own record repeatedly. The orbit tightened with each Venus flyby. The first flyby occurred on October 3, 2018, just 52 days after launch. 3 trajectory corrections were needed in that narrow window. The second flyby came in December 2019, the third in July 2020. Each encounter with Venus slowed the spacecraft relative to its orbit around the sun, pulling its closest approach ever nearer to the solar surface. And on December 24, 2024, it made its closest approach yet. Christmas Eve. The spacecraft dove to within 3.8 million miles of the sun's surface, hurtling through the corona at approximately 430,000 miles per hour. That is fast enough to travel from Philadelphia to Washington, D.C. in 1 second. It was the fastest any human-made object has ever moved, nearly 3 times faster than the Helios 2 record from 1970, 676. The exact time of closest approach was just before noon, coordinated universal time, but the probe was out of contact. The sun was between it and the Earth. The team could do nothing but wait. A beacon transmission on December 20 had confirmed the spacecraft was healthy going in, but the pass itself was silent. 2 days later, on December 26, a beacon tone arrived. The spacecraft had survived. Detailed telemetry followed on January 1, 2025. Parker Solar Probe was healthy, its heat shield had held, And the data it was carrying back was from a place that, as one NASA official put it, humanity had never been before. To fully appreciate what that means, consider the journey it took to get there. Over the course of 6 years, the probe completed 24 planned orbits. Each orbit was an elongated ellipse, swinging far out toward the orbit of Venus and then plunging back toward the Sun. Within each orbit, the spacecraft spent only a short window, close enough to take scientific measurements. During those early orbits, the science phase lasted about 11.5 days. By the final, closest orbits, it had shortened to about 9.5 days. The rest of each orbit was devoted largely to transmitting data back to Earth. Even that was not simple. Communication is interrupted when the heat shield comes between the antenna and Earth. And when the probe is near the Sun, even if the antenna has a clear line of sight, the Sun's radiation can overwhelm the signal. There are long stretches of every orbit where Parker Solar Probe is completely on its own, silently gathering data, autonomously protecting itself, waiting for the geometry to align so it can phone home. And yet, despite these constraints, the mission has returned far more data than anyone expected. The spacecraft's instruments have been kept active for more than 75% of each orbit, roughly 8 times longer than the original plan. So what does it look like inside the Sun's atmosphere? What did the instruments actually detect? The first major discovery came early. During its initial dives toward the Sun, the field's instrument suite detected something unexpected. The magnetic field carried by the solar wind was not smooth. It was full of sudden, violent reversals. The field lines would snap backward on themselves, like a zigzagging mountain road, then straighten out again. Scientists named these structures switchbacks. Switchbacks had been detected before, decades earlier, by the Ulysses spacecraft as it flew over the Sun's poles. But no one had seen them this close to their source, and no one expected them to be this common or this powerful. Parker Solar Probe encountered roughly 1,000 of these rogue magnetic waves in the solar atmosphere. Some were powerful enough to instantly accelerate the solar wind by as much as 300,000 miles per hour. In some cases, they completely reversed the direction of the local magnetic field. That is not a subtle effect. That is the Sun's magnetic field flipping like a switch. And it happens constantly. The first research papers describing these findings were published on December 4, 2019, covering the spacecraft's first 2 close passes. They confirmed a hypothesis that a type of magnetic wave known as Alfvén waves are the leading candidates for explaining the mechanisms behind coronal heating. The switchbacks themselves generate heat that warms the corona. But where were these switchbacks coming from? During its 6th flyby, the field's instrument found the answer. The switchbacks aligned with magnetic funnels on the solar surface, structures that emerge from between giant convection cells called supergranules. These are enormous bubbles of hot plasma, each one thousands of miles across, that rise from the Sun's interior, spread across the surface, cool down, and sink back in. At the edges of these supergranules, the magnetic geometry becomes complex, and switchbacks appear to originate through a process called magnetic reconnection, where opposing magnetic field lines collide, break apart, and reform in new configurations, releasing energy. This is a significant finding. It links the solar wind directly to its sources at the very base of the corona. The solar wind is not simply boiling off the surface. It is being actively launched by magnetic events happening at the Sun's visible surface, the photosphere. Meanwhile, the SWEEP instrument suite was measuring the particles themselves. One of its key components is the Solar Probe Cup, a Faraday cup that peeks out from behind the heat shield directly into the sunlight to catch charged particles as they stream past. The grids on the front of this cup reach temperatures of about 3,000 degrees Fahrenheit. They glow red while making measurements. The cup uses sapphire pieces to electrically isolate its internal components, and at closest approach, it takes up to 146 measurements per second to capture the velocity, density, and temperature of the Sun's plasma. What Sweep found at the Alfvén critical surface confirmed a suspicion that had been lurking in theoretical models. The Sun's rotation does not just spin the surface, it slings plasma outward. The data showed a surprisingly strong sideways velocity component in the plasma, much stronger than expected. The Sun is effectively throwing material off the corona in a rotating whip effect, powered by its own spin. Then there is the camera. WISPR, the wide-field imager for solar probe, takes optical images of the corona and the inner solar system. And WISPR made a discovery that astronomers had been chasing for nearly a century. Back in the 1920s, astronomer Henry Norris Russell predicted that somewhere close to the Sun, there should be a zone where cosmic dust simply disappears. The intense sunlight should heat dust particles until they vaporize. Scientists looked for this dust-free zone for decades. No one found consistent evidence it existed. WISPR saw it. As Parker Solar Probe flew closer to the Sun, the light reflected by cosmic dust began to dim at about 19 solar radii from the Sun, roughly 8 million miles out. The dust was thinning. Models based on these observations suggest that a fully dust-free zone begins at about 5 solar radii, around 2 million miles from the surface. A prediction that had gone unconfirmed for almost 100 years was finally supported by direct observation. WISPR also delivered a surprise that had nothing to do with the Sun itself. It captured the first complete view of Venus's orbital dust ring, a collection of microscopic dust particles circulating along Venus's orbit around the Sun, spanning nearly the full 360 degrees. Earlier missions had caught glimpses of the ring, but Parker's sensitive cameras and unique vantage point revealed it in its entirety for the first time. Scientists estimate that the dust along Venus's orbit is about 10% denser than in neighboring regions. And during flybys of Venus, the spacecraft detected natural radio emissions from the planet's atmosphere and even captured images of Venus's nightside surface in visible wavelengths. Another first. Then there are the energetic particles. The instrument suite called IS, which measures the fastest particles escaping the Sun, solar energetic particles that can travel the 93 million miles to Earth in just minutes, overturned most of what scientists assumed about these particles. They are more common than expected. They include a wider range of particle types than expected, and their paths from the Sun are not straight. They get disrupted by the switchbacks, sometimes traveling twice the expected distance before reaching deep space. By detecting these events so close to their source, the instrument picked up tiny particle bursts that would be completely undetectable by the time they reached Earth. An entire population of small solar energetic particle events, invisible from our planet, was revealed for the first time. And in September 2022, something happened that no one had planned for. The first comet ever discovered in Parker Solar Probe images was identified by a citizen scientist named Peter Barrett. The comet, designated PSP-001, had actually been captured in images from May of that year. Since then, 20 sun-grazing comets have been found in the probe's data, including 3 that do not belong to any known comet family. A spacecraft built to study the Sun was also, quietly, becoming a comet hunter. But perhaps the most unexpected observation came from that record-breaking Christmas Eve flyby in 2024. During the pass, Parker Solar Probe's WISPR camera recorded a solar flare erupting from the Sun. A bright cloud of superheated plasma burst outward into space, exactly as scientists predicted. This is called a coronal mass ejection, one of the most violent events in our solar system. When a coronal mass ejection hits Earth, it can disrupt power grids, scramble radio communications, interfere with satellite navigation, and light up the sky with vivid auroral displays. But what happened next was not predicted. The plasma drifted outward, began to thin, and then changed direction. Some of the material curled back toward the Sun. It made a U-turn. Strong magnetic fields pulled the erupted material inward. The returning plasma followed magnetic field lines that had snapped apart during the eruption, then rapidly reconnected into new configurations. Some of these new magnetic structures stretched outward into surrounding space. Others looped back and stitched themselves to the sun. What the probe was witnessing was the sun recycling its own eruptions. Material that had been violently expelled was being drawn back in, dragged along by collapsing magnetic loops. Scientists described these as inflows, streams of plasma falling back into the corona. Earlier missions like SOHO had observed hints of these inflows from far away. But Parker's proximity revealed the process at a scale and clarity never seen before. Scientists were able to measure the speed and size of individual blobs of material as they fell back into the sun. These measurements are now being used to refine space weather models. This matters for a very specific reason. When that plasma falls back, it reshapes the local magnetic field, and those changes to the magnetic field can influence the trajectory and intensity of future eruptions. A coronal mass ejection that might have struck Mars could, because of this recycling process, end up missing it entirely, or one that would have been harmless could be redirected. Small changes in the corona's magnetic configuration can have outsized effects across the entire solar system. The sun is not simply throwing material out into space. It is engaged in a constant, dynamic exchange with its own atmosphere. Magnetic energy is released, recaptured, reorganized, and released again. And this process is happening on scales that we are only now beginning to measure. In 2024, the probe also detected something that had only ever been theorized, a phenomenon called a Kelvin-Helmholtz instability occurring during a coronal mass ejection. This is a kind of wave that forms at the boundary between two fluids moving at different speeds, like the ripples you see in clouds on a windy day. Only here, it was happening in the superheated plasma being ejected from the sunday. It was the first spacecraft to directly observe this long-predicted event. Every 88 days, Parker Solar Probe swings back through the corona, gathering fresh data from the most extreme environment any spacecraft has ever survived. Understanding this recycling process is not merely academic. Our civilization is increasingly dependent on technology that is vulnerable to space weather. Satellites, power grids, aviation communication systems, GPS navigation, all of it can be disrupted by a sufficiently powerful coronal mass ejection aimed at Earth. The better we understand how these eruptions form, how they evolve, and how the sun's own magnetic field reshapes them after they launch, the better we can predict when and where the next one will hit. Parker Solar Probe is not just exploring the sun, it is building the foundation for a practical warning system that could one day protect everything we have built. And then, in 2025, a discovery was announced that may explain the oldest mystery in solar physics: the corona problem. The sun's surface temperature is roughly 10,000 degrees Fahrenheit, but the corona, the atmosphere sitting above the surface, reaches over 1,000,000 degrees. That makes no physical sense at first glance. It is like walking away from a campfire and finding that the air gets hotter the further you go. Scientists have puzzled over this paradox for decades. For years, the leading explanation involved turbulence. As energy cascades from large disturbances down to smaller and smaller scales in the solar wind, it eventually dissipates as heat. This is how turbulence works. In water, in air, in any fluid, energy breaks down into finer and finer motions until it converts into thermal energy. But in the solar wind, the plasma is so thin that particles almost never collide. Without collisions, there is no ordinary friction, no viscosity. So the usual mechanism for turning turbulent motion into heat does not apply. Something else must be going on. Using data from Parker Solar Probe, a team led by researchers at Queen Mary University of London found evidence of a phenomenon called the helicity barrier. This had been predicted in theoretical work, but never directly confirmed in the solar wind itself. Here is what it means, in simple terms. In the turbulent plasma near the Sun, energy cascades from large disturbances down to smaller ones, just as it does in any turbulent system. But at a certain scale, around the size at which individual ions orbit magnetic field lines, something unusual happens. A barrier forms. The energy cannot continue cascading to smaller scales in the usual way. Instead, the blocked energy piles up at that intermediate scale, and that pile-up fundamentally changes how the energy is released as heat. Instead of smoothly heating everything equally, the barrier forces the energy into a different channel, one that preferentially heats ions over electrons. This produces a very specific signature. Protons in the solar wind end up hotter than electrons. And that is exactly what has been observed in the solar wind for decades, but never satisfactorily explained. Until now. The researchers found that the helicity barrier becomes fully active under conditions that are common in the solar wind near the Sun. When the magnetic field energy is high relative to the thermal energy of the plasma, and when there is a significant imbalance in the turbulent waves propagating in opposite directions along the magnetic field, the barrier forms. These conditions are frequently met close to the Sun, precisely where Parker Solar Probe is making its closest measurements. The implications extend beyond our own star. Many other astrophysical plasmas throughout the universe are similarly thin and collisionless. Nebulae, accretion disks, the gas between galaxies. Understanding how energy becomes heat in these environments has consequences for how we model processes across the cosmos. The solar wind, observed up close by Parker Solar Probe, has become a natural laboratory for physics that governs plasma behavior everywhere. The Parker Solar Probe and the European Space Agency's Solar Orbiter have also been working together. In 2022, the two spacecraft coordinated observations to study why the corona is so much hotter than the surface. Solar Orbiter observed the Sun from 140 million kilometers away, while Parker simultaneously flew through the corona at a distance of about 9 million kilometers. In 2024, both probes made their closest approaches at the same time, allowing scientists to directly compare remote imaging with in-situ particle measurements. These joint observations are building a multi-scale picture of the Sun that neither mission could achieve alone. Coordinated observations have also been conducted with the SOHO and Stereo A spacecraft, each providing a different vantage point, a different piece of the puzzle. For the first time, scientists can track solar, wind, and transient events from their origins on the Sun's surface all the way out into inner interplanetary space. What was once a collection of isolated snapshots is becoming a continuous, three-dimensional understanding of how our star behaves. And this is what makes the helicity barrier discovery so important in context. It does not just explain one anomaly. It connects small-scale plasma physics at the level of individual ions to the large-scale properties of the entire solar wind. The variability of different solar wind streams, the temperature differences between fast and slow wind, the reason ions are hotter than electrons, all of these long-standing puzzles now have a coherent framework that ties them together. The barrier changes depending on local conditions, which means the heating of the solar wind is not uniform. It shifts and adapts, driven by the turbulence and magnetic geometry of each region. Like the Sun itself, it is restless. Parker Solar Probe was not designed to last forever. The primary mission included 24 solar orbits shaped by 7 Venus flybys. The final Venus flyby occurred on November 6, 2024, at an altitude of just 317 kilometers above the planet's surface, the closest of any of the 7. That flyby set the spacecraft into its final, tightest orbit, an 88-day loop that brings it to within 3.8 million miles of the Sun's surface before swinging back out toward the orbit of Venus. The primary mission ended in 2025. but the spacecraft continues to operate. Additional passes are being planned for 2026 and beyond, formally under NASA review. As of today, March 11, 2026, the probe is on its 27th perihelion, its 27th closest pass through the corona. But eventually, the fuel will run out. Parker Solar Probe uses thrusters to maintain its attitude, keeping the heat shield precisely aimed at the sun and its antenna pointed at Earth. Without fuel, it cannot hold those orientations. And when the shield drifts, sunlight will reach the instruments. The plan for when that day comes is straightforward. Mission controllers will rotate the spacecraft so that its instruments face the full radiance of the sun for the first time. The extreme radiation is expected to ablate and destroy them, but the heat shield will survive. That 4.5-inch slab of carbon composite and carbon foam is expected to continue orbiting the sun for millions of years. A human-made object circling our star long after everything else about it has burned away. In 2025, the teams from NASA, Johns Hopkins Applied Physics Laboratory, and their partners were awarded the Collier Trophy for their achievements on the mission. Eugene Parker did not live to see it. He died in March 2022 at age 94, but his name will circle the sun for as long as that shield endures. Now, it is worth stepping back and considering what this mission has actually accomplished. We sent a machine into the atmosphere of a star. We measured the boundary where the sun's grip on its own material finally lets go, and found it wrinkled with spikes and valleys shaped by coronal streamers. We watched magnetic fields flip and snap hundreds of times in the space of a few orbits. We saw cosmic dust vanish as it approached the sun, confirming a prediction nearly a century old. We mapped the orbital dust ring of Venus in its entirety. We caught the sun recycling its own explosions, pulling erupted plasma back into its atmosphere. We detected the first Kelvin-Helmholtz instability in a coronal mass ejection. We discovered 20 comets hiding in the data, and we found a hidden barrier in the turbulence of the solar wind that may finally explain the oldest paradox in solar physics. Every answer has raised new questions. Every orbit brings fresh data from a place that, just a few years ago, we had never been. Parker Solar Probe carries that memory card beneath its antenna. Over 1 million names. Photographs of the physicist who predicted the solar wind 60 years before the probe launched, and a copy of the paper that started it all. All of it, circling the sun at 430,000 miles per hour. The probe is still collecting data, still sending it home, still flying through a place that should be impossible to visit. It has already ushered in what NASA calls a new golden era of space exploration, bringing us closer than ever to unlocking the sun's deepest and most enduring mysteries. We touched the sun, and what we found there is stranger, more dynamic, and more beautiful than anyone imagined. For now, all we can do is keep watching. Because the more we learn about our star, the more we realize how much we still do not know. And that is exactly how science moves forward.